Welcome, everyone. My name is Dawn Mullally, and I am the Communications Manager for UCAR.CPAESS. And this position affords me the pleasure of working with many of our wonderful scientists, like today's guest speaker. I am delighted to have you attend the CPAESS Discovery Seminar Series. CPAESS scientists do everything from explore our ocean depths to fly into hurricanes to heliophysicists modeling coronal mass ejections, and those who unravel the mysteries of the Arctic. And we want to share all of this with the public, the NCAR, UCAR community, and our many colleagues at universities and agencies across the globe. So just to orient you, we are using Slido so that you can pose your questions to our speaker. You will be able to find access in the tab at the top left of the screen. So today, it is my sincere pleasure to introduce to you today's speaker, Dr. Waqar Younas, who is a UCAR-CPAESS scientist researching as a NASA Jack Eddy Postdoctoral Fellow hosted in Boston University. His research focuses on ionospheric irregularities, GNSS scintillation, and storm time impacts on satellite-based navigation. His work combines multi-instrument observations, physics-based modeling, and large-scale GNSS data sets to understand how space weather disturbances degrade positioning accuracy over the continental United States and polar regions. Since the May 2024 geomagnetic event that served as a wake-up call, revealing pronounced ionospheric irregularities and significant degradation in positioning across the continental U.S., Waqar will use this talk to highlight the broader implications for GPS-dependent systems and the growing need for improved monitoring and forecasting abilities. Today, Dr. Younas will share his recent work in this seminar called Ionospheric Irregularities and GPS Positioning Errors over CONUS: What Recent Storms Reveal About Mid-Latitude GPS Vulnerability. Please join me in welcoming Waqar.
Yeah, thank you so much, Don, for a kind introduction. And it's my pleasure to be here talking for CPAS Discovery Seminar. So let's start with the I would like to start with the thanks to all my colleagues at various institutes, and this is not a complete list, but I would like to thank all of those with whom I have been collaborating from last couple of years. This work would not have been possible without their support and collaboration. So, space weather originates at the sun, and the sun is emitting. Apart from the light, there is a continuous stream of particles we called solar wind. But this solar wind comes to the Earth and interacts with our magnetic field and create this shape we call magnetosphere. But and then there are a lot of interesting aspects of the space weather, and it could impact the various regions. But in this work, we are particularly interested in this layer of upper atmosphere spanning from 60 to 1,000 kilometers of the height in altitude. And so this we are interested to how this different kind of activities on the sun and in the magnetosphere can create and disturb this upper atmospheric layer called ionosphere, and how this could impact the different lives of the different peoples and the different regions of the earth. So let's have a brief introduction. How can the disturbances in the upper atmosphere have impact on the humanity and even different technological systems? So I'm here showing a schematic diagram here of the ionosphere. This you can see here the GPS satellites are moving around 20,000 kilometer of the altitude, and this layer is about 62,000 kilometer of the height. So there are various height structures, but you can see this layer can create a delay to the GPS signals from coming from satellite to the receiver. So receiver could be a geodetic ground receiver used for geolocation. This receiver can be on the airplane for continuous monitoring, or anything one based on satellite based navigation has these kind of GPS receivers or GNSS receivers to use for continuous monitoring of the location and timing. But for quiet time conditions, this ionospheric layer impact could be minimized either using a dual frequency combination or with the help of some reasonable models. But whenever there is a storm, it can create from storm, I mean geomagnetic storm. So it can create some sort of irregularity structures in the ionosphere, and these small scale structures disturb the shape of the signals coming to receiver. So eventually the measurements made to calculate the position and timings are not precise. So we call such structures irregular ionospheric irregularities or the scintillations. So eventually whenever these observations are not precise, it creates a error in the position. So this is the whole impact of the space weather in terms of navigation. So we have been known this kind of impact to the GPS community or GPS field from last many years. But what is new for today's seminar? So this is a schematic diagram of Bezo 1998 and 1988 paper. It shows the probable region where these irregularities could occur. You can see here, this is the magnetic local time. So the most probable region where these irregularities or scintillation can occur is the equatorial region, probably after the sunset, most likely due to the equatorial plasma bubbles. And there are also some localized regions of these irregularities in the aurora oval, cusp, and per cap patches in both hemisphere. But you can see this historic figure didn't have any probability in the mid latitude region. So from by mid latitude I mean a magnetic latitude of the 30 to 60 degree. So this region was not expected to host any sort of irregularity structure. So it was not being focused in the initial years of ionospheric research. But this from last couple of years, especially in the solar cycle 25, we have seen very intense geomagnetic storm, and several users in the continental US, which is again in the mid latitude region, mostly of the ionosphere, they reported disruptions to their equipments. So one of such example is here an article in New York Times showing that the farmers in the Midwest region reported disruptions in their tractors on 10th May when they were that was a peak season for their corn seeding, and this disruption led to significant loss to the farming community. One study later on reveals about 500 million damage to the farming community. So this indicates that the GPS vulnerability at mid latitude due to space weather can be significant and can cause significant loss. So this is one aspect, but there are any other fields like aviations. Many aviation flights were redirected to the lower latitudes, and they have been delayed, and that also has significant financial impact. So my work for today's seminar is being focused to what kind of irregularity structures can develop in the mid latitude region, and what are the trends and patterns so that we can use them to make regional models. So the tools I will be using mainly ground-based GNSS and GPS data. So for the analysis of ionospheric irregularities and remote sensing of the ionosphere, I will be heavily relying on these different tools. So one is the phase fluctuation. So this comes basically the GPS observations gives us two main things. One is the phase of the signal and other one is the amplitude. So the phase fluctuation index, or we also call sigma phi index, this basically gives us how much fluctuation in the phase of the signal when it passes through the ionosphere. So the another one is the amplitude scintillation or amplitude fluctuation index, and this is basically normalized intensity of the normalized intensity of GPS signals. It could be either at different frequencies L1 or L2. So to see the what kind of structure is in the ionosphere, we are using this TC estimation to map the ionosphere, and this comes from the dual frequency GPS receivers. So basically we calculate that slant TC along the line of sight of GPS receiver to the satellite based on pseudo range measurements, and to get the precise scale TC measurements, these slant TC are leveled to the carrier phase measurements. To analyze the impact of these irregularities and scintillation, I will be using the position error, and for these are geodetic receivers across the US. So the position errors are being estimated with the difference between the actual known position of the receiver from the position calculated from the data. So the whenever there's a difference, we mark it as an error bit due to the ionosphere after removing all other errors. So let's start with the May storm. Like I mentioned earlier in the introduction, that this storm has significant impact in the US sector. We are now using 1 Hertz GPS data, and here I'm showing some interesting snapshots of the ionosphere over the US during this May 2024 storm. Panel A correspond to the pre-storm scenario. This B is the showing a few hours after the arrival of CME. Then it comes a trough around 22 UT. This was around the before sunset, or when US was on the dust side, and this is again night side ionosphere over the US, showing some localized enhancements. So again, I would like to say that this is the time and probable region where the farmers have reported disruptions in their equipments. So you could see here there was a strong gradient in the ionosphere. One side was about 150, 160 TCU, and other side of the northern side was looking at, or in the panel C, about 10 to 20 TCU, and there we can see a huge gradient was coming to the low latitude when this traffic vertebral boundary was pushing coming to the expanding to the low latitude. So let's see how the signals behave when it pass through these different phases of the storm. Again, I'm showing the same snapshot, but at now data is being replaced by the sigma phi and the phase scintillation. So you can see the pre-storm, all are the blue dots here. This indicates that the signals are very good and very precise as there should be. But whenever the SED comes over, some small fluctuations could be seen in the northern side of the US, but the large and intense fluctuations are essentially occurring at the this equatorial boundary of mid-latitude trough. And again, as mentioned, this was the time and the region where the farmers were experiencing disruptions. So it looks like on 10th May, around the dust side, this trough mid-latitude boundary was most problematic, causing disruptions to the farmers. But there was also some localized enhancement, and we in the night side, which is being associated with the substorm related precipitation. It also created very intense fluctuations in the northern sides, but it's more pronounced on the east coast. So eventually, let's have a look on these position errors. So I am now showing the same snapshots, but the PPK mode of position error is being intentionally shown here because this mode was being used by the farmers. Panel A pre-storm errors are less than 1 meter and very precise for navigation or any kind of application for high precision systems. But here we can see just after the arrival of snowman, there was not significant fluctuation in the signal, but the ionosphere was non-uniform. So, but this is because this is not a standalone positioning mechanism. It depends on the reference station and the rover. So errors grows up, but the large errors essentially occurring at the moment when this trough equatorial boundary was moving to the low latitude. So this shows that the on 10th May, the more problematic region and the more problematic source of disruption at mid latitudes were trough equatorial boundary. But on 11th May, when US was on the dust side, on the night side, the substorm related precipitations have created significant disruptions. So I am now here marking two different, three receivers, but showing the two data from two to see how the spatial temporally these irregularities evolves. One is receiver P046 in the northern US and one is in the central KSU1. So here I am showing data from two receivers as I mentioned. So on the top, it's the storm intensity index called SYMH, then TEC, phase fluctuations called sigma phi, S4, and PPK error. So here different colors correspond to different GPS satellites. So, and this is same data from the same kind of data for different receiver called KSU1 in the central US. So you can see just this is line mark the arrival of CME, and few hours after the CME there was SCD enhanced density, and then all of a sudden it goes down when trough equatorial boundary was coming to the low latitude. So some localized enhancement in TEC can also be seen at the dust side around 2-6 UT. So, but large phase fluctuations and widespread phase fluctuations could be seen at this trough equatorial boundary, and it also has fluctuations in the amplitude of the signal, indicating there were some small scale irregularities to create diffractive scintillation. The errors actually grows up much earlier before the onset of scintillation when the ionosphere becomes non-uniform. But interesting thing here is that when we move from this northern station to the one in the central US, the width of phase fluctuation due to at the equatorial boundary has reduced, but its amplitude increased. So this shows that the irregularities at the equatorial boundary were growing at this boundary was drifting to the low latitude, and also we can see some amplitude fluctuations at this central US receiver, which essentially this leads to an error of the order of 30 meter. So this shows that the trough equatorial boundary irregularities associated with trough equatorial boundary were growing when it was coming to the low latitude, and substorm precipitation has also caused significant errors in the position as well as in the phase fluctuations. So this indicates that there were three sort of main drivers in creating disruptions at mid-latitude during Gannon storm. SCD creating the stage to increase the density, and then trough comes in, which creates a large density gradient, eventually creating gradient drift instability and large phase fluctuations. Okay, so we all enjoy the many of you have also witnessed this beautiful aurora colors. And the good thing about this large storm is that we don't need to go to northern regions or in the Alaska, Canada, because the auroras can be visible in the central or the southern US. But these auroras are manifestation of natures, but can also create disruptions to our technological world. And one of such impact is the creating errors in the position. So here I am showing some images from our sky camera in Missouri, and these are taken from a paper in GRL from John Foster. So you can see some bright aurora around 0206 UT, and we were able to find a 1 hertz GPS receiver very close to these images, and this is in the South Dakota ECSD. Here you can see a very sharp jump on the in the TC just within few minutes. So here this is the just in a couple of minutes TC goes up to 50 TCU, and it led to significant cycle slips in all PRNs and creating an error of the order of 10 meter. So this is another aspect of aurora brightness, and that can create so strong precipitation that the GPS signals are no can be disturbed, and the position calculations on the ground as well as in spaceborne systems can be inaccurate. Okay, so this May 2024 storm was not only one to create disruptions at mid-latitude. There were many storms in last few years significant enough to create disruptions at mid-latitude. So, but there I am showing here two storms. One is in the May, and another one is in the October. So these both are significant large storm. Their arrival time is approximately same. One arrived around 15 UT. That's I showed earlier May 2024. But this October storm arrived few hours before, around 15 UT. So the intensity was around 500 nanotesla for the May storm, and this October storm was around 300 nanotesla, but still significant. So, a purpose of bringing these two storms here is that if there is any common trends or the similarities, so we can unreveal the disruptions at mid latitude. So I am now showing the TC for both cases. On the top it's for May 2024, and the bottom one row showing the TC for October 2024. So first panel, a column indicating pre-storm scenario, then few hours after the arrival of CME, then trough at the dust side when trough equatorial boundary was coming to the low latitude, and this last panel for the night side. Main thing takeaway from this slide is that the for May storm, acidity was more pronounced on the west coast as compared to the October storm, and acidity is more pronounced on the east coast. And but the overall large scale structures are very pretty much similar. Let's have a look on the this phase fluctuations or the sigma phi. So it's these are the same snapshots, but now being replaced by the phase fluctuation. The signals are pretty good before the arrival of CME, then few fluctuations at the SCD, but the large irregularities occurring at the trough equatorial boundary coming to the low latitude. As I mentioned, for the October storm, SCD was more pronounced on the east coast as compared to the maelstrom, and that's impact of the SCD, that the phase fluctuations occurring more relatively high on the east coast as compared to the west coast. This indicates that the potential role of SCD creating location of where the more enhanced phase fluctuations could occur. But the substorm related fluctuations can also be seen for both storms. So here now let's have a look at the Spatiotemporal evolution, comparison of the spatiotemporal evolution of irregularities during both storms. And on the right side, I'm showing October. On the left side, May storm. You can see there is SCD, trough-equatorial boundary, and the substorm related T scene fluctuations and phase fluctuations can be seen for both storms, but the errors are large for the October storm for this particular station, and this could be related, associated with the more enhanced irregularities for this P802 receiver in the North Dakota. But when we move from the northern to the central receivers, one is here I'm showing the Kansas, like I showed in earlier slides. For October storm, this one is P44 in Colorado. So trough equatorial boundary has more irregularities for May storm as compared to this for this October storm, and here is a potential role of SCD for the October May storm. We have seen the SCD was high as compared to the October ones. So this high SCD creates large gradients at the trough equatorial boundary, leading to strong phase fluctuations and position errors. So we can see that when these large phase fluctuations occurs, the position algorithms have to drop those satellites, eventually leading to an outages. And then this PPP mode of positioning took very long time to converge before the end of the day. So it shows that besides the lot of similarities between two storms occurring in the same local around the same local time, but there are still significant differences which could create difference in the location and intensity of irregularities. Okay, so one can wonder that, okay, these are the only ones irregularities we can see at mid latitude, but that's not true. Sometimes storms, if the arrival time is different, the impact at mid latitude could be very different. So for this purpose, I am bringing another storm that's for November 2025. So you can see here the a storm here in for this case arrived around 0 UT, and very different from May and October, and this created very intense precipitation, creating very strong phase fluctuations and phase sigma amplitude in the due to the expansion of aurora oval. But there is also some localized enhancement coming from the low latitude, which created a narrow band of irregularities penetrating deep in the US sector. So this indicates that the location as well as timing of the irregularity could be very different depending upon the different arrival time of CME. Yeah, so like for May storm, we have seen, sorry, for this October storm, we have seen there was some strange kind of irregularities in the low latitude, coming from the low latitude region, which has a very strong amplitude and phase fluctuation. So that's called nighttime ionospheric localized enhancement. This is not a new one. This has been reported in the solar cycle 23 when some intense storms occurs in 2003, 2004. Here I am showing the one of the earliest paper on similar topic from Sivani, and that shows that this is pretty much localized enhancement, and because initial study shows this is mostly in the Florida region. Some people called it this is a Florida effect. But recent studies, like one for May 2024, has shown that similar kind of structures could develop in the other longitude sectors, such as Chinese region, where this paper shows that the similar kind of nighttime ionospheric enhancement was occurring. But I am now focusing on very different event where this kind of enhancement occurs in relatively moderate storm, but with the unprecedented level of TC with a very severe scintillations in phase and amplitude. So that's the January 2026 storm. So this I'm showing this Madrigal TC four panels. First one is pre-storm. Then this is the snapshot around the midnight for the main phase of the storm, and this is the day after the main phase, and this is the very second day after the main phase. But you can see a very severe enhancement over the American longitude, and that's coming. I will show later. That's coming from the low latitude, but it's happening not on even during the main or early recovery phase, but in the late recovery phase of the storm. So just get you an idea about the what phase of the storm I am talking about for this particular case. I am now showing that on the top it's different geomagnetic activity, global solar wind indices. Then this is AE showing the electrojet inputs, and the bottom one is SOMH index. And on the right side, I am showing medical TC focused over American region, and with the gray side showing the night and brighter one showing the day side. So let's have a look on this movie. So you can see this the region when the storm arrived. Then we don't see any sort of nighttime enhancement even during this main phase of the storm, and intense fluctuations were happening, but the strong perturbations in the density occurs just after the moment when these are conventional geomagnetic activity indices has subsided. So just have a look at this Caribbean sector. You can see a blob of plasma coming from the low latitude, and that quickly moved to the penetrated deep in the continental US region. So this shows that the sometime a very late effects of storms could occur, and that may have not been seen for through conventional geomagnetic activity indices. But is this was just a density enhancement, but are there any small scale structures which can create disruptions to a wide community of GNSS? So I am now showing the 1 Hz GPS TEC on the top, and bottom one is again AE and SOMH index, and this line indicating the phase of the storm where we are looking. So there was a SED. SED is daytime enhanced density that mapped from the mid latitude to the polar region, and you can see this SED has passed around the dust side, but this structure I am talking about for this storm is pretty much different from the SED. It appears after the this passing of this SED, and it has a very intense TC, and I will show later that it was more about 200 TCU, and then it was initially appear in the Caribbean region, stayed little bit there, then moved quickly to the Florida and penetrated into all over this narrow band of in the continuous US. So I will let's have a look at the is this an just a density enhancement, or it create has some intense phase fluctuations. So I am now showing on the top this 1 Hz GPS measurements phase fluctuations, and on the on the left side S4. So you can see there is no significant fluctuations due to SCD, but the large fluctuations in the GPS phase as well as amplitude occurring just at the moment when this density enhancement was coming from the low latitude, and it was pretty intense, and we have not seen this level of disruptions even during the May and October storm. And this shows that the structures could be different, and their impact could be very different depending upon the different mechanisms that are causing them. So this indicates that very intense fluctuations happening due to this Nile kind of density enhancement during the late recovery phase of this January 2026 storm. So some people may think that this may not look real because this was very strange density enhancement, very in the very strange region. So we were lucky to have a 50 Hz GPS receiver in the Florida, and that receiver also captures these structures. So I'm showing here on the top measurements from this 50 Hz GPS receiver: elevation, vertical TC, then L1 sigma phi, L2, S4 L1 and S4 L2. Purpose of bringing this L sigma phi and S4 measurements from L1 and L2 was that if it's due to the some RFI artificially produced things, then it should be more pronounced on L1 as compared to the L2. But for the ionospheric effects, it should be more pronounced on lower frequency, which is L2. And as you can see that both sigma phi and S4 have higher amplitude for L2 as compared to the L1, then this confirms that this was actually in the ionosphere that created intense disruptions during January 2026 storm. So let's have another look on this event. When swarm make a pass through this density enhancement. So I'm now showing a background, this 1 Hz GPS TC on the black line showing the trajectory of swarm satellite starting at 510 to 520 UT. So here is on the left side is the data from the swarm satellite. On the top, TC, S1, elevation, in situ plasma density, and the temperature. So this structure was not in the lower ionosphere, but it was high enough in the that the swarm satellite lost the lock. You can see here, and it also has the in situ observation from swarm satellite revealed some depletions within this large scale structure, and this again indicates that there were some bubble like structures coming from the low latitude, and this enhanced density in the Nile has amplified its impact. So just another look on this January 2026 Nile event. On the right side, I am showing the GPS TC from a receiver in the Puerto Rico. This is the elevation, TC, phase fluctuations, and amplitude fluctuations. You can see here the TC was fluctuating dramatically. Even for one receiver, some satellites showing 200 TCU at the same time, other satellites showing almost 10 to 20 TCU. And when we map this all receivers in the Puerto Rico to a all sky imager showing air glow 630 nanometer, and this shows that these structures in the all sky imager and TC are well coherent. This again confirms that these disruptions, as there were pretty small scale irregularities on January 21st and during this late recovery phase of the storm, and that confirms the bubble like small scale irregularities were present in this Nile event that has caused a widespread disruptions in the continuous US. Okay, and so I will now quickly go to the possibility of from these things we learned from these case studies. So, if we look on the case-to-case basis, we can see there are some significant similarities and some differences. But if we bring the data from all the cases, then we may be able to create some sort of regional forecasting models. So, here you can see we have done a kind of a survey to and understand the occurrence probability of phase fluctuation, and they took all the data from the onset of the storm to the recovery phase and calculate the percentage occurrence of phase fluctuations above zero point 0.1 radian. So this is one storm for I'm showing November 2025 case. We can see the enhanced occurrence probability in the northern region, probably expansion of due to the aurora oval and the trough, and some localized enhancement due to the bubble-like structures coming from the low latitude. But when we look on the several cases through this occurrence probability, then we can understand the role of several drivers and complexity of the system we are looking. So I'm now showing the four cases. One is the May 2024, October 2024, this November 2025, and also I'm showing the peak SOMH for each case, and also this September 2017. So you can see that this one was the intense storm in couple of decades. It has most intense equatorward progression of this irregularities due to expansion of oval and trough equator boundary, but we didn't see any sort of bubble-like feature during this storm. During the May storm, October storm, the this disruption due to the auroral precipitation and trough was less as compared to the May, but it also has some localized enhancement due to the irregularities coming from the low latitude. And same thing happens to the this November storm. But there are some outliers. There are some strange storms like the one I'm showing here, September 2017, when the storm intensity was not comparable to these ones, but still it has significant disruptions in both from the Aurora region and also when these bubble-like structures comes from the low latitude. So it needs some larger data sets to make a statistical analysis to understand the role of different drivers creating these irregularities. So we have now recently started the superposed epoch analysis. This analysis is basically we considered all the storms less than 100 nanotesla and then mark them, align them with the minimum SOMH values. So there are around 137 such storms. So, so we have started working on this, and it looks like arranging the data in magnetic time would be more beneficial to get idea of the different local times when these structures or irregularities occurring. So I am now showing the first listing of this superposed epoch analysis with the cases from 100 to 200 SOMH non-Tesla SOMH. So we have identified around 100 such storms starting from solar cycle 23, 24, 25. So from movie here you can see I'm now showing the magnetic latitude and magnetic local time. This is the noon and this is the midnight. This mean TC coming from all these 100 moderate storms, and this is the phase fluctuations. So this superposed epoch is this is the time around with respect to the SOMH minimum. So you can see the expansion of aurora oval just at the time when we hit the minimum SOMH value, indicating the potential role of expansion of aurora oval, and also some localized enhancement in the dust side region, probably indicating the role of bubbles coming in the narrow MLT window. So we have also tested these things for the For large storms like the one 200 to 300 nanotesla, there are not too many, but still enough to indicates that the analysis could cover the whole MLT sector. So you can see some enhancement in the phase fluctuations, and so due to the expansion of oval, some trough related expansion at the pre-sunsets region, but some strong fluctuations are also occurring in this uh, post sunset to midnight region, probably indicating that's a region where the bubbles can come into the mid latitude sectors. So this one is the last category with the superstorms having intensity less than 300 nanotesla. We didn't have too many such storms, and that's why we couldn't cover the full MLT range for this category of the storm using the data from continuous US. So it's made in the future we can take the data from other longitude sectors such as Europe or the Asia, but we can also incorporate the observations from other constellations such as GLONASS, Galileo to fill these gaps, and so that these modeling efforts or the forecasting can be improved. So I have running short of time. So we have got a good interest from the community and the users. The research presented here has also been listed from various agency and media outlets. You can look into these news and more details about these works. Last thing, we are also convening AGU session on ionospheric irregularities. You can look into if you are planning to come into this AGU 2026. You can submit your abstract. Here is the complete list of articles I used for today's seminar. You can look into more details of these papers. Yeah, so that's all the summary. We have been able to identify the main sources of irregularities at mid-latitude. There are similarities and differences in different storms, but superposed epoch analysis, the initial results are promising, and it looks like it has capability to merge with different forecasting parameters like SOMH or any solar wind forecasting, so that we can in future prepare to mitigate such impacts due to the space weather. Yeah, that's all I have.
Thank you so much for sharing your work, Waqar. We truly appreciate it. Now we will begin the question and answer portion of today's seminar. I'd like to direct everyone's attention to Slido to ask your questions. Either you can use the QR code or the tab in the upper left corner of your screen. While you are doing that, I would like to invite you to check out our webpage, cpass.ucar.edu, for our upcoming seminars. Our next scheduled seminar is on August 19th, 2026 at 11 a.m. Mountain Time with Dr. Pratik Mayank, who is also a NASA Jack Eddy Postdoctoral Fellow, and he will be speaking on how AI is transforming solar wind research and forecasting. So please go to our website for details. You are also invited to check out this talk and past talks on CPASS's YouTube channel, and you can find a link on our webpage. Okay, let's see if we have any questions. Oh, we do. I'm sorry, I don't want to butcher this name, so I'm just going to say, thanks, doctor, for this great presentation. If one changes the mask angle for the TEC computation to below 20 degrees, is it likely to influence the results greatly?
Yeah, so yes, you can cover the more special area, but there are some hurdles. Like if you go to the much lower mask angles, elevation angle, then it can make more noise due to the multipass. But some sophisticated or the wideband signals such as L5 have shown robustness to the multipass. So, but if it's a clean estimation of the TEC, having coming from the low elevation can be beneficial.
All right. Um, Please put in your questions if you have any questions. In the meantime, actually, Waqar, I'm going to ask you, so I'm going to pull way out to much broader vision. First of all, let me just say I appreciate the fact that you do work that is um so it's so surgical with how important solar storms are and how it affects our world. But I am okay. I'm gonna jump to one more question here. Sorry. Um, but I'm gonna pull back in a second. So
Sure.
another question from the same lovely person on the GNSS data availability. Have you faced the challenge of data gaps during the different storm phases over the different stations of study? Is it okay to consider a station with data for some parts of the storm phases? Thank you.
Yeah, for the US sector, we do have a good coverage of the because it's a pretty dense network of GNSS receivers all over the US. But if there is like a question that if there's someone studying on other region and if there is data gap in some receivers, we can consider that data which is available and used for your analysis. It's not necessary to have a, it's good to have a complete data for a full storm, but it's not necessary you can take if it's as consistent with the other observations.
Right. Okay, please put your
Yeah.
questions in. But I will just to kind of pull back for somebody who does not have your scientific specialty. You started off the talk by mentioning the May 2024 storm. So just to be really clear with folks who are not scientists like yourself, all of this is very important because space weather impacts things on Earth, in particular GPS and other things like that. And you had mentioned with the New York Times article that there's $500 million damages to farmers. Can you tell us like what kind of how did that work? How did GPS affect farmers
Yeah.
financially?
That's interesting question. So the farmers in the US are using precision agriculture technique to seed and for their agriculture applications. And this 10 May was a peak season for the corn seeding. And we talked to the different farmers in the Midwest region, and some of them told that we just that's autonomous tractors they are using for seeding, and they give the instructions. Okay, go to this field and put your go to this field and seed these corns, but they intentionally go on to the other side of the field or go walk around, and they were totally lost. They didn't know what was happening, why this is happening. They talked to the companies who have those tractors, but they were not aware that it's actually something in the ionosphere, or it's due to the sun that has emitted CME earlier that day that is creating disruptions in their equipments. So yes, with the going and growing days, we are heavily relying on these technological systems and GNSS-based autonomous vehicles, drones. Then this impact could go much beyond these agricultures.
That's wonderful, Ricard. Yeah, I can see how I didn't realize that farmers were using autonomous vehicles to seed their crops. And so if the GPS is all messed up, then like you were saying, they were literally in left field or they were not seating at the right place. That's
Yes.
And I can also see how that's going to be increasingly important with more autonomous vehicles and, like you said, drone technology and stuff like that, that everybody's using more and more. It looks like our friend who was joining us is from Uganda, Africa. So thank you so much. We really appreciate that. Um, do we have other? Sure. Um, Here we have, as continual improvements are so important, what approaches do you think should be pursued next?
Yes, like I mentioned in last few slides, we are now doing a superposed statistical analysis to uncover the some mysteries that we still know the some structures or the features which can create these kind of disruptions, but still there are some unsolved issues. But if we bring the large data sets, combine all available storms data, then we may be able to better understanding of this response of the ionosphere and disruptions to GPS, and that may help us to nowcast, creating nowcasting or forecasting models.
Anything else? Okay. And we have another question from our friend in Uganda. From the combination of the signals, what's your say on L1 plus L5 combination for the TEC computation?
Yes, any combination can be used as long as it's coming from two different frequencies, but because L2 and L5 are wideband signals, so they are not suspected to the multipass as the L1. So I suppose say the L2, L5 may give us better result, but it entirely depends on the receiver's location, its antenna. Multipass have very different behavior for each receiver where the antenna is located. So it's nice to have a look on the data before the days before the storm. So if you can see the similar kinds of disruptions occurring on even quiet days or the before the storm days, then it could be some multipath issues, not the in the TEC.
Okay, and we have another question from Mohammed. During major geomagnetic storms, which ionospheric irregularities contribute most significantly to GPS positioning errors over mid-latitude regions, and how can modern GNSS systems or correction techniques be improved to reduce these errors?
Okay, yeah. So, as from our current understanding at mid latitude, it looks like the trough equatorial boundary has a most intense impact, and it because it comes just before the dusk, and it can be more problematic to the most users. So, since these are the irregularities, there are multiple ways to address or the reduce these errors. One could be the like better cycle slip corrections, but if the impact is so strong, then this making the receiver's robustness can also be a better way so that they can continuously track the signals better way.
That's wonderful. Um, Before we wrap up, Waqar, since there's so much interest in your wonderful research, do you have an email address where people can contact you or some place where they can find some of your research?
Yes, there is email. I didn't put it on my presentation, but uh, W Younas, my second name, and first name W Younas at the rate of bu.edu. They can reach out to me with anything I presented today.
Thank you so much. And I really appreciate, I don't understand everything that you're researching, but I really appreciate the impact of it because it really matters and it's going to become increasingly important.
Yes,
Um,
thank you so much.
So we are going to wrap things up for today. Thank you for everyone for coming to the UCAR-CPAESS Discovery Seminar. And remember, you can visit our website, cpaess.ucar.edu, to find out about future talks. Here you can also find out about past talks, including this one, and where to find it on YouTube. Waqar, a sincere thanks to you for sharing your important work with us. And also, thank you to CPAS staff, Alex Meyer, along with Fletcher Ryan of UCAR Multimedia Services for their invaluable assistance. I hope to see you all at our next CPAS Discovery Seminar, and have a wonderful afternoon, everyone.